Hi, can you hear me now? Hello, should we start? Hello. Okay, great. So, just what I was explaining before the break, I want to conclude it without, you don't have to think much about mathematics, but what actually we are doing, well, that's what I want to tell you. Because we have already discussed all these things in our previous lecture. That is not important for us now. But what I'm trying to say is that we started with the Bayes theorem, right? We started with the Bayes theorem. Bayes theorem was like pH given what is the maximum probability, what is this, we have to maximize this probability, and this probability is nothing but PD given H into P of H upon PD. We want to maximize this expression. What is that hypothesis that is maximizing this expression among a space? So this is equally probable, we are ignoring it. This is constant term, it doesn't matter, it will not affect that have it is in the selection of hypothesis. So these two terms are ignored now. So once these two terms are ignored, we are left with P D given H. I said that my data is nothing but D1 D2 D3, right? Since this data, because of mutual independence, this data was now break into this expression P D1 given H, P D2 given H, up to let's say P D n given H if there are n points. So we have to maximize this expression now. After maximizing this expression, what got? We got this expression. So we started with Bayes theorem. We come on this expression after simplifying and maximizing this expression. After simplifying and maximizing this expression, we left with this one. So this expression is maximized if I will choose my hypothesis in such a way that the sum with di, the difference of my hypothesis that I chose and the value that it is giving for that particular xi should be less. The difference is less. How you can visualize it? For example, I have these three data D1, D2, D3. So I should choose my hypothesis that must minimize these differences. If I got the one hypothesis, the hypothesis that is minimizing these differences is the maximum likelihood or map hypothesis in our assumption. So on now other way, if you want to see it, somebody comes and asks you to minimize directly the difference of the errors, right? You want to minimize the sum of error. Definitely, by Bayesian analysis, every time you minimize the sum of errors, it is nothing but you are picking that hypothesis that is most maximum probable, because Bayes theorem, by using Bayes theorem, you have already see that. So this minimizing the sum of error is nothing but a way to choose a hypothesis that is maximum probable, that is mostly probable, maximum probable among the set. This is what I want to say from this slide. Okay, so what is minimum descriptor length principle? At first, before introducing this topic, I first want to introduce some term entropy. What is entropy means? Entropy means that what are the expected number entropy mean the formula of entropy, though we can discuss it in half, we can take half an hour for this discussion, but in short, the formula of entropy is pi log base 2 pi. This is a negative sum. So if there the negative sum, so the graph of log is like this. So this is 1, because probability cannot probability cannot be greater than 1. So we will take that graph up to the point 1 only, because now when I take the negative of this log, this is this one, right? So what this expression is saying, this log p to I, log base 2 pi, is saying that if I want to send a message I, let's say there is a message I want to send, this log base 2 pi minus is giving me the optimal number of bits that I should use to code that message. What what I'm trying to say is, for an example, you have three numbers in your message, 1, 2, 3. Now the that probability of 1 is zero point 0.9. It means in this message 1 appeared much more times than this 2 appeared. Let's say 2 appeared now point 0.05, and this 3 appeared also 0.05. So this 2 appeared, this 3, and this 3 appeared. Now this is a message 1 2 1 2 1 3 1 1. You want to send this message. So the anisotropic principle says the number that is having maximum probability, you should use the minimum bit for it. For an example, if I have three numbers, I can represent 1 by 0 0, I can represent 2 by 0 1, and I can represent 3 by 1 0. Right? These are the three notations I can take. Now in this case, if there are 10 numbers, let's say if there are 10 numbers, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. If there are 16 number, so how many bits I'm sending? 16 into 2 equals to 32. But if I want to be smart and I want to send less number of bits, is there any way to do that? Yeah, if I can use one bit for one, uh, I can, let's say I have in the short way. This is not a good example. In short way, the probability for the number which is which is most probable, I should use minimum bot for it, and the number which are less probable, they rarely appear, I can use the more number of bits for their representation. Likewise, every time I want to send a frequent number, so the frequent number can be sent by using small number bits, but the rare number can be used to represent by a large number of bits. So this anotropy principle says that uh, if you want to send a message, if you want to represent a message that is having ith message that is having a probability p, if there is a message I that is having a probability p of a so you can represent that message by using log base 2i number of bits, and minus is for the positive number because log is negative here, right? This is a negative side. When you take the negative of this graph, you come to the positive side. So this expression is saying that the optimal number of bits that you want to use to represent the ith message is directly proportional to the inversely proportional to the probability. The more probabilities, if it is having the the more probabilities when you go to this side, the less number of bits you want to use to represent that number, the less probabilities when you going to this side. So you can use larger number of bits also. So this is a bits, let's say, and this is the probability. So the more probability it is, the number of bits you want to use less. The less probabilities, the less probabilities probable it is, you can use a larger number of bits because it is very rarely appeared. That is what anatropy means here. So what this minus log pi stands for, minus log pi stands for. So now just come to this expression, but you know that how you can represent H map. You know this, right? I don't have to repeat again how you come with this H map. This is a prior probability. This is a likelihood. Yeah, that is the product. You're ignoring PD in it. You want to maximize this expression to find out what is that hypothesis that is maximizing this expression. You are taking now. It is same when you take the log of it. The log, when you take the log of it, this is the expression that you get. Now when you take you are maximizing this expression But if you take the negative of this expression, you want to minimize this expression to find out the maximum a priori hypothesis. So you want to minimize this expression because you have taken the negative of this expression. This you have taken the negative of this expression. So this expression comes, you want to minimize it. So the the hypothesis that is minimizing this expression is your map hypothesis. Now we will try to understand we can what we can conclude from this expression. Okay, so this minus log base 2 pH, this minus log base 2 pH, right? This is the probability of representing my hypothesis. This is the probability of my hypothesis, pH. And this log base 2 pH is nothing but this expression is saying how many bits I should use to represent this H hypothesis. The more probable it is, I should use the less number of bits. This is a probability, right? If you just relate this expression to this expression, the more probable it is, the less bits you want to use. So this hypothesis probability will tell you how many bits you should use to represent this. So for just sake of simplicity and understanding, you can assume that this you can write hypothesis in terms of like ones and zeros, or in some terms of code, or you want to write in text, let's say. So you want to describe you want to write some hypothesis. So the more the description length of that hypothesis is given by this expression. It is only for understanding, right? It is only for understanding. I want to correlate this expression with this expression. So this expression is saying that these are the number of bits I want to represent to represent that my hypothesis. And this number of bits minus log base 2 PD given H is the number of bits that I should use to describe the data given hypothesis. That are the optimal number of bits. If the number of bits that I'm using to describe my data given hypothesis and the number of bits that I'm using to represent my hypothesis, if I want to minimize this expression, this minimizing of expression is same that I'm moving towards the representation of that hypothesis that is most probable. I will take an example. I will tell you what it is. So introduction to a basic result of information theory. Consider a problem of designing a code C to transmit a message drawn at random. Let's say you want to transmit a message from a sender and a receiver. So there is a sender and there is a receiver. So the sender, you want to transmit a message, you design a code that is transmitting a message. Probability of encountering a message I is Pi. I already discussed it. Interested in the most compact code C. What is that most compact code? That is that should describe that hypothesis in a very minimum length. So Shannon and Weaver showed that optimal code length is minus log .ai. We don't have to prove it, but they have shown that this is the optimal number of bits that somebody should use to represent that message, if that message has a probability P. So I am representing the description length of a message I with respect to C. So what this is saying, this is a length or description length of that message I when I'm using that code C. So LCH is nothing. The length CH is the optimal code for hypothesis H. when I am representing my hypothesis with some code, when I am representing, and this LCDH is where CDH is the optimal code for designing the data using that both the sender and receiver knows the hypothesis. My H map is nothing but it's a min of this length sum plus this length sum. Don't get confused. I will come with an example. So let's describe an example. So for an example, you have a decision tree, and let's say decision tree is of this width. Let's say decision tree is of this height. So decision tree means when you come to the node where it will ask you some question, yes or no. Whether it is yes, you go to this side. If it say no, to this side. And for an example, this decision tree accuracy, and it is classifying, then let's say this is class C1 and this is class C2. If you end up to this node, then it classify class C2, and if you end up to this node, it classify class C1. So if you have a decision tree of this height and you classify some examples, then the accuracy is, let's say, 0.5. If you want to increase this accuracy, you have to increase the depth of it to get a better accuracy. Now you are saying, for an example, it may say that yes, and for yes it may come to this node, and for no it can sit to this node. But again, there may be some other attributes which you want to classify. Let's say for x1 you are saying yes or no, and other next time you are classifying x2. For x1 you come to this side, for x2 you come to this side. So for x1 yes you come to this side, for x1 no you come to this side, for x2 yes you come to this side, for x2 no you come to this side. Now this is C1, let's say this is C2, C1, C2. Now the accuracy of this classification will be increased, and let's say this is 0.7. So in short, you don't get confused by like what is decision tree. I will explain a lot, like I will take a whole lecture, 2-hour lecture in some future session. But for now, I want to explain you what is minimum descriptor length. It means, in short, if the height of a decision tree is less, then the accuracy is also less. If the height of the decision tree is large or big, then the accuracy of classifying the numbers is also better. So this is how you can take a decision tree right now. So when I have some decision tree, I want that decision tree which should be short. I want to take that decision tree using to take this expression. This is my hypothesis, right? This is my hypothesis. I want that decision tree which should be short, because that short tree will minimize this expression, because this is the length of a decision tree, let's say, and this is the classification of a decision tree. So if I want to minimize this whole expression, and this is the height of a decision tree, or this is the size of a decision tree, so the less decision tree I will take, it will finally minimize this expression. But the trade off is this: when you take shorter decision trees, the classification using those decision trees will be less accurate. Therefore, you need more number of bits to represent the accurate classification. But if you take larger decision trees, then you can classify much better. Then in that case, this expression will get short, but this expression will get large, because you are taking the larger decision tree. So your ultimate aim is to finally minimize the sum of this. So this minimum descriptor length principle is trying to say that you should choose the hypothesis in such a manner that it should be very short. It should be very simple. It would be very simple means, if you take example of line, this you can describe this line using only two parameters, that is W0 and W1. If you take an example of nth ninth order polynomial, then you need W0, W1, W2, W3 up to W9. So these number of description length, for to describing this number of length, this number of parameters, you need larger number of bits. So what this max minimum descriptive length principle is saying, you should choose the hypothesis in such a manner that those so that it can be described using less number of bits. But other term also available there that is saying how you are classifying the data using that hypothesis. If you are using very simple hypothesis, like if you are using a line and you want to classify this number of bits, this number of data, so the line will not define this number of data very accurately. But if you take this and ninth order polynomial, it will describe this data very accurately. So if you use very short hypothesis, it will misclassify the data samples. But if you take large hypothesis, it will accurately classify the samples. But what is that point? What is that point that will minimize both? That means minimize the whole expression. That point is actually the uh, maximum priority hypothesis. So I know that it is not clear because I think you should read this topic once or twice from that book from Tom Michel, and in further we will discuss it on a forum so that you can have a better understanding. So I encourage you to all you guys to read this minimum descriptor length from Tom Michel chapter 6, and we will have a big discussion on the forum so that we can understand it more accurately than that. So again, what I was saying, that if you have a tree, that if let's say you use a tree with a shorter length, right? Now if you use a tree with a shorter length, so you can represent this tree with less number of bits, right? But when you use this less tree, the misclassification error will get high. For an example, you want to send these number of x classification. You want to send from sender to receiver the hypothesis and the classification. So if you use less hypothesis, like a shorter hypothesis, you can send these hypotheses with less number of bits. Now this hypothesis will go to the receiver side. Now receiver also know the hypothesis, and sender also know the hypothesis. Sender and receiver both know the hypothesis now because it is already sent there. Now if you want to send this classification accurately, so because he know the hypothesis, he don't need to send every classification to the receiver side. He need to send only those examples there which are actually misclassified, because the correctly classified examples, he have a hypothesis at the receiver side. He can use this hypothesis to classify that example x, because it is actually correctly classified to the sender side also. But if some example that is misclassified the sender side, he will send that example ID. Let's say this is a third example and it was classified as a positive. So he will send this two information, and let's say there are other example that is 7 that is misclassified as a misclassified, so its correct classification is negative. So you want to send these two examples also along with the hypothesis. So at first he sent the hypothesis. Now he is sending these two things also that are misclassified by the hypothesis, because sender knows what is the correct classification, but receiver don't know what is the correct classification. In that case, every misclassified example need to be sent to the receiver side and its actual classification. So if you use the larger hypothesis, then the classification error will be 0. So sender need to send only the hypothesis at the receiver side, and because he used a larger hypothesis, he don't need to send any misclassification error, because there are no misclassification error because he already used a larger hypothesis descriptor length. But if he use a shorter hypothesis description length, in terms of description length, then there would be misclassified errors also. In that case, along with the hypothesis, he need to send those misclassified examples plus their actual classification. So this is a trade-off, and that trade-off you should the trade-off is you want to optimize this expression, and MLTM principle provides a way for the trading off hypothesis complexity for the number of error committed by the hypothesis. Can you please give the example of HMDL where both LCH and CDH are no, 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 no. Both cannot be minimized. If you increase one thing, that other thing will be decreased. For example, you use the larger trees. Larger trees. In that case, you can describe this larger tree with a more maximum number with larger number of bits. But misclassification error will get reduced to zero, right? Misclassification will get reduced to zero in that case, because this is the larger tree and you can classify, you can use this tree to classify every sample correctly. Now in that case you have to send this larger tree to this side, that is LCH. It take larger number of bits to send to the receiver side, it to the receiver side. But if you take a shorter tree, let's say this is a shorter tree, when you send from sender to the receiver, it takes less number of bits to send. But because it is not classifying every example correctly, you need to send those examples with their correct classification also. Now it takes extra burden to that. What is that optimal point where you should choose the hypothesis and the misclassification error so that you can send a minimum number of bits to from sender to the receiver? That optimal point is correspond to the maximum H map, and it is also dealing the overfitting also. You can because if you use the larger trees that overfit the data, and overfit the data means that every data is, you know what is overfitting, right? um, say I honestly say that this is a little different than the regular notions, so you can have a little more time to understand it, but it is not that hard. You should first go through that and take your time, re-listen this lecture, and we will discuss it on a forum so that you have a better understanding there, right? So for now, I just want to finish this lecture, and you just read it. And we will. If you have any query, you can start some discussion on that forum, and I try to address it. So Bayes optimal classifier. What is the most probable classification of the? So the now we know that there is a classification that we can do using a map, hypothesis, or MLE, maximum likelihood Bayesian thing. But can we improve further? Can we improve further? Because whatever the hypothesis you take, HMAP or HML, maximum likely, it is not always guarantee that it classifies the sample correctly. It guarantees that it can do best among all the given hypotheses, but it is not guaranteed that you cannot do much better than that. So what is that thing where you can do much better? Like what is the most probable classification for the new instance given hypothesis? Let's take an example here. So there are three hypotheses, H1, H2, H3, and the pH given D, H1 given D is 0.4, pH2 given D is 0.3, pH3 given D is 0.3. Now you can see given a data to see the hypothesis is maximum in this case. So H map is this. H map is equals to H1. Consider a new instance X encountered which is classified positive by H1 and negative by H2. So there are three hypotheses, H1, H2, H3. Map is saying that this is that best hypothesis which is having a probability high, right? But it is classifying some given sample as positive, and the remaining two hypotheses classifying the given sample as negative. Now, if you consider all the hypotheses all together, you can see that the probability that is favoring for a positive classification is only 0 0.4 in this case, and the probability that is favoring for the negative classification is 0 0.3 plus 0 0.3 is 0.6, 0 0.6, right? So here you can see that if you consider all the hypotheses all together, you can do much better if you only consider HMAP. The most probable classification is to obtain by combining the predictions of all hypotheses weight by their posterior probabilities. So it is nothing, just to I directly come to the example. So this is P H1 given D. This is what I already told you in the example. PH2 is the PH2 given D is 0.3. PH3 given D is 0.3. So HMAP obviously is this because it is the maximum among all. Now H1 is classifying a given X. A given X is there, and X1 is classifying that X as positive, and the same X is classified by H2 as negative. So H1 is classifying this X as positive, and H2 is classifying that the same X as negative, and H3 also classifying the same X as negative. So in that case, the corresponding probabilities are 0, 0, 0. What is the probability? What is the overall probability that goes in favor of the positive classification? That positive classification comes with like probability of positive given H1, probability of H1 given data, plus probability of positive given H2 into probability of H2 given data. Wait, I will address it. Plus P positive given H3, P H3 given data. In that case, P, you can see this expression is 0, so it will goes to 0. This expression is also 0, it goes to 0. So the remaining thing left is 0 0.4. That's why this expression says that the positive classification, when you use every hypothesis, is the probability is getting 0 0.4. Similarly, when you use same example and you weight that example with the probability, with the hypothesis probability is 0 0.6. So this is larger one. So what this expression is saying, that the expression that is having the larger probability in favor of that X, you should choose that classification, right? So this slide is saying that this is the V means plus, V could be positive or could be negative. So what is the probability of Vj? Let's say positive. Vj is positive. What is the probability of positive given data? So you are doing the same expression and you calculating that the probability of positive given data is using these hypotheses is 0.4, and when you're using probability of negative given data, using this expression is 0.6. So you are taking the max of this. Max of this is 0.6, so you are doing that point negative. What I mean to say in Bayesian optimal classifier is that you take every point at a time to see that point with every, you go to every hypothesis and ask how you are classifying this point, positive or negative. The probability of that hypothesis itself, like what is the probability that you can see that hypothesis, and what is the probability that it is classifying that example as positive or negative. You are multiplying it, so this is nothing but a weighted sum. in statistics. So you go to every hypothesis and ask their classification, and you do the weighted sum, and finally you come up like what is the weighted sum for positive classification in probability terms, and what is the probability sum in negative class terms. Whichever the one is the maximum in positive and negative, you're classifying that sample as according to that one. There is a question, please. If you have already covered it, but what is positive classification and negative classification? Positive classification and negative classification, don't get confused here. It is just two classes, maybe class A or maybe class B, maybe class positive, maybe class negative. This is just a binary classification, 1 or 0. They are all the same, right? Binary classification it is. Positive and negative means you have to classify into one of the either one of them. So here I am considering only two classes, 1 and 0, or positive or negative or something, whatever you want. So Gibbs algorithm, finally. Now you have seen that there is a way to classify the given sample, given sample. So there is a question. So after this optimization, which hypothesis will be chosen? So yeah, this is a good question. I should speak some few lines on this. So one student is asking. So after this optimization, so this is not our optimization, right? We have already find out there are number of hypotheses in the space H. Let's say there are three hypotheses, H1, H2, H3. We know their probability also, like given D, what is the probability of that H1, given D, what is the probability of H2, given D, what is the probability of H3. Now there are three different probabilities, H1, H2, H3. Posterior probability we know 0.4, 0.3, 0.3. I am not optimizing it now. I'm not optimizing. I am taking a one sample. I want to classify it. I just go to the first hypothesis and ask how you're classifying this example, positive or negative. It is saying, let's say it's positive. But what is your value? If you are saying that it is positive, how much probability you have? You have, like H1 is having a 0.4 probability. So by 0.4 probability, H1 is saying it is positive. Now I go to the H2. It is saying it is negative. And what is the occurrence of H2? It is zero point 0.3. So 0.3 probability it is saying negative. Take that same example and go to H3, and H3 is saying it is negative with 0.3 probability. Finally, I come up that in the whole space, the vote towards the negative classification, the weight, not vote, the weight towards the negative classification is more than the weight towards the positive classification, because in the space positive classification is zero point 0.4 and the negative classification is 0.3. So for that classification of individual point, I am just considering and going to every hypothesis and asking and doing the weighted sum of it. Whichever the weighted sum is higher, either for positive or negative, I am classifying it. So in this case, I am not taking any individual hypothesis, right? So it is the optimization in terms of classification. It is not the optimization in terms of picking the hypothesis. I'm not choosing only one hypothesis here. I am just asking to every hypothesis, and depend upon the probability of that hypothesis, I am taking that, I am considering that value or that weight towards that. So don't get confused. So which hypothesis will I am choosing? I am going to every hypothesis, right? So according to the probability of that hypothesis, I am choosing, I am giving the weight to it. This is the weighted sum. So there is other question, will there be a courseware for ML? So I'm really confused about it. What do you mean by courseware? There are some lectures that is being recorded. Okay, let's first finish. Let me finish this PPT first. This is the last one, I hope. So now you have seen that there is optimal classifier is there. You can do Bayesian optimal classification is there. And Bayesian optimal classification algorithm says that go to the every hypothesis and ask that what is the classification they're doing for that classification, weight according to their probability, and finally come up with some classification positive. This is the optimal one. But so I'm just reading the slide now. Note the base optimal classifier provides the best result, but it can be expensive if there are many hypotheses. Let's say there are 10 million hypotheses in a space, or 1 million, or let's say 1000. You go to every hypothesis and ask what is your classification, and see what is the probability of that hypothesis, and waiting to it, and finally concluding for positive and negative. Let's say this is positive. For every X you are doing that. For every X you are going and asking to each. That this is expensive process. What Gibbs is saying, what Gibbs is saying, that let's say this is the space of the hypothesis, and this is a distribution they are following according to this pH given D. This is the posterior distribution. Let's say this is a maximum likely H1, and sorry, HX. This is again less likely. This is HZ, and this is, let's say, HY. So this is there could be some distribution. It is not, I have drawn it like in similar to normal distribution. It could be any type of distribution. It could be any distribution. But because we generally discuss normal distribution, so that's why I'm considering it normal distribution. So it can follow any distribution. What Gibbs is saying in his algorithm, he say that you pick any hypothesis according to the distribution, posterior distribution, and classify according to that hypothesis only. What that hypothesis is saying, just believe that that hypothesis is correct. Dramatically or surprisingly, when you choose only one hypothesis from the distribution, according to the distribution, the error that you get by Gibbs algorithm is not more than twice the optimal classification. So for an okay, so what this Gibbs is saying? Gibbs is saying that choose H at random according to the posterior probability distribution. And if you just to focus you here, I want you to get attention, take attention on these words. What do you mean by posterior probability distribution? Because the likelihood they will be choosing according to their probability, right? Because this is, if it is, this is the probability distribution that the H space is following, and you want to pick some hypothesis in it, because it is this hypothesis is having this maximum likely. So the probability of choosing this hypothesis is more than the probability of choosing this hypothesis, because you are choosing at random according to the distribution. If you don't understand this line, go and see how you can choose a number according to the Gaussian distribution, or how can you generate a number according to the Gaussian distribution. Then you can understand what it is. Like for a given distribution, you can pick a number at random. So when you have a posterior distribution, probability distribution over H, you just pick a random H according to this distribution and classify that X, new X, using that hypothesis. You will surprisingly see that the error that you get by Gibbs is not more than twice the error that what you get by Bayes. That's what. Okay. Finally, I just covered this. I couldn't recall what the session it is, but this whole chapter of chapter 6 is divided into 2 sessions in your course handout, and I have taken like most of it. In the next class, I will be taking Bayesian belief networks, in which I will be completing expected maximization and Bayesian bias variance trade-off, and finally that will be, and also I will be taking decision trees. So in the next 2 lectures, I will be taking Bayesian belief networks and decision trees. and I hope that most of that will cover. And finally, we will be finishing that linear regression part, what is left out, and that will make like 50% of it what we have done so far. So what I want to